In this video, we'll cover the basics of gravity. As a refresher, what is gravity and why is it significant? Gravity is simply the force that attracts two mediums that have mass and is a vector quantity as encompasses both magnitude and direction. Gravity is a very crucial piece in natural phenomena as is the force that is able to pull objects towards Earth's surface and ensures that objects aren't just simply floating in the air. Gravity exists in every nook and cranny, such as between your body and the floor, or between a book rested upon a table. Gravity is actually very intricate in terms of the mathematical and arithmetic functions needed to be performed to calculate it. However, the goal of this video is to take an introduction about this. What formula should we get familiar with when calculating gravitational force? The formula for calculating gravitational force follows as the gravitational force is equal to the universal gravitational constant times mass 1 times mass 2 divided by distance squared, in which F represents the actual gravitational force between any two mediums that have mass and is measured in newtons, or N. G represents the universal gravitational constant, which is 6.67 times 10 to the minus 11 newtons times meter squared divided by kilogram squared. M1 and M2 represent the mass of mediums 1 and 2 measured in kilograms, or kg. R represents the distance between the centers of the two mediums of mass, measured in meters. Now let's do a few practice problems to apply this intricate formula. Number 1. Calculate the gravitational force between the bowling ball, denoted as object 1, and the bowling pin, denoted as object 2. So we're given that object 1, the bowling ball, has a mass of 4.5 kilograms, and object 2, the bowling pin, has a mass of 1 kilogram. We're also given that the distance between the centers of the two masses is 6 meters. Now that we have all the information we need, we can simply plug them into the gravitational force formula, which states once again the gravitational force is equal to the universal gravitational constant times mass 1 times mass 2 divided by distance squared. First, let's write out the ratio for the universal gravitational constant as 6.67 times 10 to the minus 11 newtons times meter squared divided by kilogram squared. Now let's plug 4.5 kilograms as mass 1, 1 kilogram as mass 2, and 6 meters as r. To simplify this, we would multiply 4.5 kilograms by 1 kilogram to get 4.5 kilograms squared, and 6 meters times 6 meters to get 36 meters squared. Notice that the kilograms squared and the meters squared cancel out as they are both in the numerator and denominator of this problem. With that said, we're just left with Newton, or N, which is the unit we want in the end, as it's the unit that gravitational force is measured in. Now the problem simplifies to 6.67 times 10 to the minus 11 newtons times 4.5 divided by 36. When we plug this entire ratio into our calculators, we should get an approximate value of 8.34 times 10 to the minus 12 newtons. Thus, the gravitational force acting on these two objects is approximately 8.34 times 10 to the minus 12 newtons, in which both objects are attracting one another with the same force but in a different direction. Number 2. Calculate the gravitational force between a 14 kilogram block, denoted as object 1, and a 7.5 kilogram ball, denoted as object 2. So we're given that the distance between the centers of the two masses is 10 meters, and we're given that object 1, the block, has a mass of 14 kilograms, and object 2, the ball, has a mass of 7.5 kilograms. Now that we have all the information we need, we can simply plug them into the gravitational force formula. So first, let's write out the ratio for the universal gravitational constant as 6.67 times 10 to the minus 11 newtons times meter squared divided by kilogram squared. Now let's plug 14 kilograms as mass 1, 7.5 kilograms as mass 2, and 10 meters as r. To simplify this, we will multiply 14 kilograms by 7.5 kilograms to get 105 kilograms squared, and 10 meters by 10 meters to get 100 meters squared. Notice that once again the kilograms squared and the meter squared cancel out as they're both in the numerator and denominator of this problem. With that said, we're just left with the Newton, or N, which is the unit once again we want, since this is what gravitational force is measured in. Now this problem simplifies to 6.67 times 10 to the minus 11 newtons times 105 divided by 100. When we plug this into our ratio into our calculators, we should get an approximate value of 7.00 times 10 to the minus 11 newtons. Thus, the gravitational force acting upon these two objects is approximately 7.00 times 10 to the minus 11 newtons, in which both objects are once again attracting one another with the same force but in a different direction. Number 3. Calculate the gravitational force between Earth's surface, denoted as mass 1, and a 60 kilogram person, denoted as mass 2. So we're given that mass 1, the Earth's surface, has a mass of 5.97 times 10 to the 24 kilograms, and that mass 2, the person, has a mass of 60 kilograms. We're also given that the radius between the person and Earth's center of mass is 6.38 times 10 to the 6 meters. Now that we have all the information we need, we can simply plug them into the gravitational force formula, which states once again the gravitational force is equal to the universal gravitational constant times mass 1 times mass 2 divided by distance squared. First, let's write out the ratio for the universal gravitational constant 6.67 times 10 to the minus 11 newtons times meter squared divided by kilogram squared. Now let's plug 5.97 times 10 to the 24 kilograms as mass 1, 60 kilograms as mass 2, and 6.38 times 10 to the 6 meters as r. To simplify this, we would multiply 5.97 times 10 to the 24 kilograms by 60 kilograms to get 3.582 times 10 to the 26 kilograms squared, and 6.38 times 10 to the 6 meters times itself when we square it to get 4.07 times 10 to the 13 meters squared. Notice that once again the kilogram squared and the meter squared cancel out as they're both in the numerator and denominator of this problem. With that said, we're just left with the Newton or N, which is the unit we want once again in the N, as it's the unit that gravitational force is measured in. Now the problem simplifies to 6.67 times 10 to the minus 11 newtons times 3.582 times 10 to the 26th power divided by 4.07 times 10 to the 13th power. When we plug this entire ratio into our calculators, we should get an approximate value of 587.03 newtons. Thus, the gravitational force acting upon Earth and the person is approximately 587.03 newtons. Once again, both are attracting one another with the same force but in a different direction. For our last problem, we'll do a word problem, a real-life scenario. So for this one, it states NASA scientists, while testing their newly constructed apparatus that was meant to gather data about Neptune's terrain atmosphere, needed to calculate the gravitational force exerted by Neptune on the Sun for an analytical datasheet to be used later on. Help NASA scientists calculate the gravitational force exerted by Neptune on the Sun for an analytical datasheet to be used later on. So we're given that Neptune's mass is 1.024 times 10 to the 26 kilograms, and the Sun's mass is 1.99 times 10 to the 30 kilograms. We're also given the distance between the centers of the two planets is 4.5 times 10 to the 12 meters. So we'll assign Neptune's mass as mass 1 and Sun's mass as mass 2. Now that we have all the information we need, we can simply plug them into the gravitational force formula. First, let's write out the ratio for the universal gravitational constant once again as 6.67 times 10 to the minus 11 newtons times meter squared divided by kilogram squared. Now let's plug 1.024 times 10 to the 26 kilograms as mass 1, 1.99 times 10 to the 30 kilograms as mass 2, and 4.5 times 10 to the 12 meters as r. To simplify this, we would multiply the two masses to get 2.04 times 10 to the 56 kilograms squared, and 4.5 times 10 to the 12 meters times itself when we square it to get 2.03 times 10 to the 25 meters squared. And notice that once again the meters squared and the kilograms squared cancel out as they're both in the numerator and denominator of this problem. With that said, we're just left with the Newton, or N, which is the unit we want in the N as it's the unit that gravitational force is measured in, like we said before. Now the problem simplifies to 6.67 times 10 to the minus 11 newtons times 2.04 times 10 to the 56th power divided by 2.03 times 10 to the 25th power. When we plug this entire ratio into our calculators, we should get an approximate value of 6.7 times 10 to the 20th newtons. So once again, both are attracting one another with the same force but in a different direction. Thanks so much for watching, everyone. I hope you guys enjoyed.